Good morning, everyone. Welcome to the My Tutor online school this morning. So good to see lots and lots of you in the session already, which is great. If you're new and it's your first time tuning into the online school, then welcome. So good to have you with us. My name is Frederica and I work at My Tutor and I host the majority of the sessions. This session this morning is a GCSE Chemistry session on covalent bonding. And it will be led by our tutor, Aman. Aman has led all the chemistry sessions so far, so if you've tuned in for them, then you'll know who she is. If not, as it says, she studies medicine at King's College London and has done over 150 lessons with my tutor. So just to reiterate, as we always do at the beginning of these sessions, remember that they're all recorded, so you won't be missing out on anything if you don't catch it in the session. You'll be able to watch it back in your own time as many times as you want. And also to say that we typically have 45 minutes of the session for Aman to deliver the content and to go through the lesson with you. And then we have 15 minutes at the end for questions. So if you send your questions through using the chat feature or using the Q&A feature, then either Aman or myself will pick them up and hopefully clarify things as and when we need to for you. Cool, so I'm going to hand over to Aman now.
Hey everyone, welcome back. So as Frederica said, today we're going to be looking at covalent bonding. I thought we'd start off with a quick recap of a cooling curve. So yesterday we looked at heating curves and kinetic theory, so I thought we'd just quickly look at a cooling curve before going into covalent bonding, simple molecules and giant covalent structures today. So just as we start then, we've got a cooling curve on the screen. So as I said yesterday, we looked at a heating curve. So a cooling curve is pretty much the opposite. So instead of going from solid to gas, which would kind of look a bit like this, so pretty much be the opposite, a cooling curve goes from gas to solid. So I thought we'd just try and label the parts on the diagram, because for GCSE Chemistry, we don't necessarily need to understand what's going on. We do just need to be able to label the parts though. So at A, we start off as a gas, and that's because the temperature is really high and gas particles have the most energy because they've got lots of kinetic energy, they can move around. We know that the spacing in gas particles is quite far, so they can collide with the walls of the container and also with each other, so with all the particles. And then the temperature is decreasing between A and B, so it's really important just to remember that when we're cooling something down, instead of heat energy going into that substance, heat energy is being released from the substance. So it's going into the surroundings from the substance. So if we're going from solid to gas, we heat it up and the heat energy goes into that solid to become a gas eventually. Whereas when we're going from gas to solid, the heat energy comes out of that gas and into the surroundings. And then we've got this plateau phase between B and C. And here the phase is condensation. So the gas is changing into that liquid, which is where we are at C. And then again, from C to D, we've got a decrease in temperature, and that again is that the liquid is losing energy. So those kinetic, or those particles are losing that kinetic energy that they have. And then we reach this phase here between D and E, and this is freezing. And then at E, we've become a solid. So that's just labeling all the parts there of what's happening in our cooling curve. And as someone mentioned yesterday, the condensation part is longer than the freezing part. And that's all to do with the bonds. So if you think about the bonds between a gas and a liquid, the gas particles are so far apart that to form the liquid bonds again is going to take a lot longer. And that's why the condensation stage is so long, whereas the freezing stage is a lot shorter because the liquid particles are already quite close together. So to become a solid, it doesn't take as much energy, and therefore the freezing phase is quite short. So that's just a quick recap of some of the phases that we went through yesterday with a look at the cooling curve and being able to label that. So now let's start with today's topic then, that's covalent bonding. So on the screen, we're I've got some diagrams of hydrogen and oxygen. Before we go into kind of the specifics of covalent bonding, let's think about what it actually is. And the first thing is it's bonding that occurs between two non-metals. So if we go to our periodic table, non-metals are on the right-hand side of this red line. So I keep showing you this periodic table, and that's just to hopefully get you used to the difference between metals on the left and non-metals on the right. So our non-metals are on the right, and covalent bonding only occurs between the non-metals. Just to say, someone's asking why there aren't any lessons on Friday. That's because it's a bank holiday. Same with next week on Monday. So in the non-metals, we don't get ionic bonding, we don't get metallic bonding, we get covalent bonding. So remember, ionic bonding, which we covered last Friday, is between a metal and a non-metal. Covalent bonding is between non-metals, and metallic bonding, which we'll be covering tomorrow, is between metals. So we're dealing with non-metals, and the other thing to mention is that hydrogen is a non-metal. Even though it's not on this side, it has lots of different properties, so it's put in the middle of the periodic table. But remember, it is also a non-metal. Okay. So let's go back to this slide then. So we know it's two non-metals, and then the other thing to think about is what's happening with the electrons. So in ionic bonding, a metal will give its electrons to non-metals, who will then gain electrons. But in covalent bonding, these elements, or these non-metals, are sharing electrons, and that's really important, and we're going to come on to what that means in the next slide. Someone's asking if you need to write this down. You don't have to. These sessions are recorded, so you can watch them back and write notes afterwards, or you can write notes as we're going along. So as I said, electrons are shared. Let's have a look at this hydrogen diagram. So we know that hydrogen has an atomic number of 1. That means its number of protons is 1, and the number of protons are equal to the number of electrons unless the atom is charged. Hydrogen isn't charged here. That means it has 1 electron, and that 1 electron is in its outer shell. So hydrogen only has 1. That means that 1 electron is in its first and outer shell. So if hydrogen wants to bond with another hydrogen atom, we know that hydrogen, to have a full outer shell, will need 2 electrons, because in the first shell, it can have a maximum of 2 electrons. So if hydrogen wants to fill that shell, it needs to share an electron to get 2. So what's happening in this diagram here is that this hydrogen atom and this hydrogen atom have shared their electrons so that they both effectively now have 2, and therefore they've both filled their outer shells. And they've said here that it's a stable arrangement and it forms a covalent bond. So let's think a bit about that covalent bond. This is a single covalent bond, and that's because each hydrogen atom is sharing 1 electron. Whereas if we look at oxygen here, we can see that each oxygen atom is sharing 2 electrons. So 2 from this oxygen and 2 from this oxygen, and therefore that is a double covalent bond. You can also get triple covalent bonds, which we're going to look at in just a second. But it's important that we know whether it's a single, double, or triple, because the amount of energy that goes into breaking those bonds increases with the strength of that bond. So if it's a triple covalent bond, it's a lot stronger than if it's a single covalent bond, for example. So let's have a closer look at this oxygen bonding. So in oxygen, the atomic number, if we go to our periodic table, is 8. That means it has 8 protons, which is equal to the number of electrons, so it has 8 electrons. Someone's asking what time does this finish? Today this finishes at 10:45. Okay, so there are 8 electrons in oxygen. So the first shell will have 2 electrons, and the second shell will have 6 electrons. So 2 plus 6 is 8. So that means if oxygen wants to fill its outer shell and get that noble gas structure, that means it needs to share 2 electrons with another oxygen atom to have 8 electrons. So that's what's going on in this diagram. The oxygen has shared 2 of its electrons with another oxygen so that they both have 8. So if we have a look at this oxygen here, we've got 4 on its own and 2 in the bonding process, plus 2 shared from the other oxygen, which makes 8. And then in this oxygen, 4 on its own in the shell, 2 shared and 2 from the other oxygen atom, which makes 8. So the purpose of covalent bonding is to get that full outer shell via sharing of electrons. And then if we think about what's being made, so what do we call this? This is known as a simple molecule. It's not a compound at this stage, because remember, compounds are made of more than one element. At this stage, a hydrogen molecule here is only made of one element, so therefore it's still an element, but we call it a simple molecule. Same with oxygen. That is also a simple molecule. This square, sorry, it's supposed to be an arrow. It's supposed to say that when we form a covalent bond, when electrons are shared, we form a covalent bond, and that is a simple molecule. Okay, so now let's have a go at drawing nitrogen, water, and methane. So if we start with nitrogen, let's go to our periodic table. Nitrogen has an atomic number of 7. So that means it has 7 protons and 7 electrons. I won't draw the full shell diagram. I will just draw the outer shell. So in the first shell, it will have 2 electrons. And then we said that the atomic number of nitrogen is 7. So that means in its outer shell, it will have 5 electrons. So I'll draw those as crosses. So remember, I do them at 12 o'clock, 3 o'clock, and 6 o'clock, and then obviously 9 o'clock if there are 8. So we've got 5 electrons here. And we've said that the diatomic molecule, so diatomic means 2 atoms. So traditionally di, written like that, means 2, tri would be 3. So that's what diatomic means. So here it's 2 atoms coming together. So nitrogen is diatomic. If we draw another nitrogen, and I'll draw this with dots. Again, it's going to have 5 electrons. So what we can see is that each nitrogen atom wants 3 electrons in order to complete its full outer shell. So if each nitrogen shares those 3 electrons, they can receive those outer shell of electrons. So someone's asking me, why are there 2 electrons in the middle? I'm not sure. Are you talking about this oxygen diagram? I was just pointing to which atoms I was talking about there. I've not drawn electrons in the middle. Sorry if that was a bit confusing. So with nitrogen then, they want to gain a full outer shell of 8 electrons. So let's share 3 from each nitrogen, because that's how much each one is missing. So if we do that, so remember, it looks a bit like a Venn diagram because we want this overlap. And then if we make this nitrogen have crosses as I've drawn, it's going to share 3. And the right-hand side nitrogen will share dots. And that's just to make it clear to the examiner that you know that one atom will have crosses and one atom will have dots in the way that it's being shared. So obviously this doesn't happen in real life, but it's just to make it clear. And then we've got 6 in the middle. This nitrogen, because it's shared 3, will have 2 left. And this nitrogen over here has shared 3, so we'll also have 2 left. Now, if we have a look at what's happening there, each nitrogen then has 6 in the middle. So this nitrogen here has 6 in the middle with 2 on the outside. That makes 8. The left-hand side nitrogen has 2 on the outside and 6 in the middle, which is 8. Now, the other thing to recognize is because there are 6 electrons in that middle, there is a triple covalent bond going on. So there's 3 electrons from each. So this is a very, very strong covalent bond compared to oxygen, which only had a double covalent bond, and hydrogen, which had a single covalent bond. Okay, let's have a go at drawing water. So if we go to our periodic table, we know hydrogen has an atomic number of 1 and oxygen has an atomic number of 8. So hydrogen is just going to have 1 electron in its outer shell, and oxygen will have 2 in the inner shell, and on its outer shell will have 6. 2 plus 6 is 8. So oxygen wants to have 2 electrons to make its outer shell, but hydrogen only has 1 electron that it can share. So that means we need to use 2 hydrogen atoms in order to complete oxygen's outer shell and fill the hydrogen outer shell. So to do that, if we draw oxygen first, and then again, similar to a Venn diagram, we want the overlap. So that's 1 hydrogen there and 1 hydrogen there. So I said that oxygen wants 2 and hydrogen only has 1 to give. So if we imagine each hydrogen then gives its 1 electron or shares its 1 electron, and oxygen will then also share 1. So if one atom shares 1, then the oxygen will only share 1. Oxygen won't share 2 if hydrogen only shares 1. So that means oxygen will share 1 with this hydrogen and 1 with this hydrogen. And then we can see they've got 4. Each hydrogen atom at the moment has a complete outer shell because it has 2 electrons, which is what it wants. And then oxygen will have 4 left. And we can see 4 plus the 4 shared makes 8. Okay, our final diagram then is methane, which is CH4. So carbon has an atomic number of 6 and hydrogen has an atomic number of 1. So if we draw carbon, atomic number of 6 means that 2 in its first shell, 4 in its outer shell. And hydrogen, as I've drawn before, only has 1. Draw that as a dot. Only has 1 electron in its outer shell. So if carbon needs 4 to make a full outer shell of 8 electrons. So remember, the second shell can have a total of 8. So to make that whole capacity, we need 4 electrons, whereas hydrogen only has 1 that it can share. So that means we need to have 4 hydrogens bonded to carbon in order to make the 8 electrons that carbon needs. So to do that, again, like a Venn diagram, okay, and then each carbon will share 1 electron. So we know it's got 4, so it will share 1 electron with each hydrogen. And each hydrogen has 1 electron in its outer shell, so it will share that with carbon. And then what we can see is that carbon now has 8 electrons in its outer shell, and each hydrogen has 2. So that's covalent bonding and how to draw the simple molecular diagrams. By simple, I don't mean that they're easy to draw, that's just what we call them. We call them simple molecules. We will be looking at the structures of diamond and graphite today. Graphene we will be looking at tomorrow with the fullerenes before we do metallic bonding. Someone is asking for the difference between a molecule and a compound, and that is a really good question. We're going to go on to that in the next slide now. So we're going to be thinking about properties of simple molecules. So first of all, compounds are made of more than one element and they must be chemically combined. So we covered that on Friday. Whereas molecules can be made of one element, or they can be made of 2 elements. So if I just go back to this slide here, we drew water. Now water has 2 elements in it, chemically combined. So technically that is also a compound as well as a simple molecule. And in exam questions, they can try and almost catch you out because you may be thinking, oh, that's a simple molecule, but it's also a compound. Whereas nitrogen is made of 1 element and therefore is only an element and a simple molecule. It wouldn't be classed as a compound. So there's an overlap. Just make sure in your head you think about molecules are covalently bonded structures. Compounds have to be made of more than 1 element and they must be chemically combined. Some molecules are chemically combined and made of more than 1 element, whereas some molecules are only made of 1 element that is chemically combined. So some molecules are compounds, some of them aren't. Okay, let's think about the properties of simple molecules. So we've talked about these strong covalent bonds that occur between the atoms. So if we think about our nitrogen, we know that forms a triple covalent bond. That's just another way to denote the triple covalent bond that I've drawn there, whereas oxygen only forms a double covalent bond. So the amount of energy that would need to go in to break that nitrogen bond is very, very strong. Someone's asking, will we need to know about lanthanides and actinides? We won't be covering that in these webinars this week. So let's think then, these strong covalent bonds require a lot of energy to break, but why do simple molecules have low melting and boiling points? So let's think about oxygen. We know oxygen's in the atmosphere and it goes around in pairs like this with double covalent bonds. The reason that simple molecules, have low melting and boiling points despite these strong covalent bonds is because there are what we call weak intermolecular forces between the molecules. So when we break these molecules apart, we're not breaking those covalent bonds, we're breaking these weak intermolecular forces, and therefore not a lot of energy is needed to break those bonds. So I'm going to repeat that again. Simple molecules, if we imagine here, this is a simple molecule of oxygen. It's got a covalent bond between it, a double covalent bond. A lot of energy is needed to break that bond. But when we melt or boil oxygen, we don't break the covalent bonds between oxygen atoms, we break the bonds between molecules. So this is just one molecule, this is a second molecule, and this is a third molecule. So remember, oxygen doesn't just go around as one molecule, there'll be lots of different molecules there. And it's these forces between molecules, which are known as intermolecular forces, and those forces are very, very weak. So to melt or boil, to melt or boil these substances, only the intermolecular forces need to be broken. And that's why oxygen is a gas at room temperature. So room temperature is about 20 degrees, which is quite low. And that means that the melting and boiling points are really low. So remember, melting takes a substance from solid to liquid, and boiling takes a substance from liquid to gas. So oxygen is a gas at room temperature, which must mean its melting and boiling points are very, very low. And it's because of these weak intermolecular forces between the molecules. So that's covered these two boxes here. The third box talks about that intermolecular forces increase with the size of the molecules. Someone is asking me, just before we go on to that, why are the intermolecular forces weak? So intermolecular forces are weak because of their name. Essentially, whenever you hear intermolecular forces, they could be quite far apart, these molecules, they could be quite close together. They're not made of electrons, it's just kind of attraction. They're attractive forces, and those attractive forces aren't very strong. So that's why intermolecular forces are always cast as weak. When we go on to the structure of graphite, we'll look at that again, because intermolecular forces are used quite a lot. And as I said, there's no kind of formal bonding that's going on, whereas we know in ionic bonding, electrons are gained and lost. In covalent bonding, electrons are shared. There's no kind of formal electron transfer that's going on in intermolecular forces. They're just attractive forces that are going on between the molecules, and therefore they're quite weak. Someone is asking, do simple molecules only occur with the two same atoms? So no. So as I mentioned, CH4, methane, is made of two different atoms there, and water is made of two different atoms. So simple molecules can also be compounds, and they can also be elements. Okay, so the third box over here in the yellow, intermolecular forces increase with the sizes of molecules. So larger molecules have higher melting and boiling points. Someone's asking, is this chemistry? Yep, we're covering covalent bonding today. So if we think about then what that's saying, intermolecular forces increase with the size of molecules. So that means as the molecules get larger, so larger molecules will have larger intermolecular forces, and therefore melting and boiling points will be larger. If you think about a polymer, polymers are solid at room temperature. They're made of CH bonds, and they can often have lots and lots and lots of CH bonds. And what that means is that they're very, very large molecules. So if they're large molecules, they have large melting and boiling points. And that's why a polymer is a solid at room temperature. So that means that its melting and boiling point must be quite high, because at room temperature at 20 degrees, it hasn't yet melted into a liquid or boiled into a gas. Whereas oxygen, which is a very small molecule, is a gas at room temperature. And the final thing to think about is that simple molecules do not conduct electricity. And the reason for that is because there is no overall charge on the simple molecules. So to think about overall charge, we need to think about what's going on in the covalent bonding. So we know in covalent bonding, electrons are shared. That means there's no kind of gain or loss of electrons, whereas in ionic bonding, metals lose electrons, so they have more protons than electrons, and non-metals gain electrons, so have more electrons than protons. In covalent bonding, electrons are shared, so there's no loss or gain of electrons, and there's no, that means that there's no charge on that molecule. And for that reason, there are no electrons available to carry any current. So remember, in ions, ionic bonding, when we melt a solid, it becomes a liquid, and so the ions can move, and that's what carries a current through an ionic bonded, so a giant ionic structure. Whereas in molecules, there are no free electrons to carry any charge, there are no ions, so that means that simple molecules do not conduct electricity. So that's kind of the 3 or 4 main properties of simple molecules. So I've got some one other thing to talk about. and that with regards to simple molecules, and that is related to whether it dissolves in water. So what this text box over here says is that most simple molecules do not dissolve in water. And the reason that I've put this on the slide is because we do need to know that they don't dissolve in water, but at GCSE Chemistry, they won't necessarily ask you why. I always think it's a bit easier to understand if we do kind of have a basic understanding of why that occurs. So just as a very basic level, because this is almost reaching into A level, at a basic level, water has a charge. Now, I've just told you that simple molecules don't have a charge because it's sharing of electrons. Water is an exception. And the reason for that is that the electrons that are shared in water, so we know it's a single covalent bond, so hydrogen here is sharing one, oxygen is sharing one, this hydrogen is sharing this one, oxygen is sharing this one. Now, the reason water has a charge is because the electrons are pulled slightly closer to oxygen than hydrogen. Normally, in molecules, they're completely shared evenly, so there's no charge. But in water, there's an exception that the electrons are slightly closer to oxygen than hydrogen. And what that means is that oxygen has a very slight partial negative charge, and hydrogen has a partial positive charge. So again, the electrons are pulled slightly closer to oxygen. That means there's slightly more electrons towards oxygen, so it's slightly more negatively charged. And so they're slightly further away from hydrogen, and therefore they have a slight positive charge. And that is why water has a charge, but most simple molecules are insoluble. And the reason for that is if something is to dissolve in water, it needs to form bonds with that water. But if we know that simple molecules don't have a charge, they can't form bonds in that water. Okay, so I've also given some examples of some simple molecules that will bond in water. So I'm getting a lot of questions from one person. Could you stop kind of sending so many messages, because it stops me from seeing other people's messages who are asking me questions to do with chemistry. So here we can see sugar and ethanol, they have an OH bond. So OH is like in water, so we know oxygen bonds with hydrogen like this. And so there's an OH bond. So if something is to dissolve in water, it must have an OH bond, which sugar, which hopefully you know from biology, so sugar or glucose and ethanol do have. So ethanol is alcohol and it's got an OH bond at the end of it. So someone's asking, does water have strong intermolecular forces and why? Yes, it does have strong intermolecular forces because water is still a molecule. So remember I said that if we think about this molecule of oxygen here, these bonds are strong covalent bonds, but water doesn't just go around as one molecule. In a glass of water, you would have lots of molecules of water. So there are these intermolecular forces between each molecule. And so when we're melting when we're boiling water into a gas, it's these intermolecular forces that break rather than the covalent bonds. Okay, so now we're going to go on to giant covalent structures. So we've covered simple molecules. The next thing to look at is giant covalent structures. But before we do that, I think it's important we know the difference between both. So most non-metals will form simple molecules, and that's what we've been covering over here. So these simple molecules, nitrogen, oxygen, water. But there are some examples, and the three examples that you need to know that form giant covalent structures are graphite, diamond, and silicon dioxide. Okay, so before we go on to going through those, I've got a quick exam question covering simple molecules. So this question says, explain why the melting point of hydrogen chloride is minus 115 degrees, whereas sodium chloride's melting point is 801 degrees. Does anyone have any ideas what bonding is going on between hydrogen chloride and what bonding is going on between sodium chloride then that might help us to answer this question? Okay, so hydrogen chloride, if we look at our periodic table, hydrogen is a non-metal and so is chlorine. Great, so someone has said that hydrogen chloride is covalent and sodium the sodium compound is ionic, which is absolutely brilliant. That's exactly what's going on. So hydrogen is a non-metal, chlorine is a non-metal. Therefore, the bonding between hydrogen chloride is covalent. Whereas the other compound, which was sodium chloride, if we go to our periodic table, sodium is on the left-hand side of this red line, so it's over here, and therefore it's a metal, and chlorine is a non-metal. So the bonding that occurs between metals and non-metals is ionic bonding. So we've got two different compounds here then. So we've got hydrogen chloride, which will form a simple molecule because of the covalent bonds. And we've got sodium chloride, which will form a giant ionic structure, or an ionic compound. So to think about the melting points then, we need to understand these bondings. So just before I go into that, someone's asking what the red line on the periodic table means. The red line is the difference between metals and non-metals. And so exactly correct, some people have said that the simple molecule hydrogen chloride has these covalent bonds, but it's not the covalent bonds that are being broken when we think about the melting point. It's the weak intermolecular forces between hydrogen chloride molecules. So this hydrogen chloride has a very strong covalent bond, but between molecules of hydrogen chloride, there are these weak intermolecular forces, and it's these weak intermolecular forces that are being broken, so these dots that I've denoted here, and that's why the melting point of hydrogen chloride is low. Whereas in sodium chloride, I'll just draw it like this, it's the ionic bond between sodium and chlorine that are broken when we melt sodium chloride. Someone is saying, I don't understand, is simple molecule the same as covalent bonding? So pretty much most non-metals will form simple molecules when they covalently bond. So covalent bonding is the type of bonding that occurs between two non-metals. And when we covalently bond structures, we can either form a simple molecule or a giant covalent structure. Most of them will be simple molecules. There are 3 examples of giant covalent structures that we need to know about at GCSE Chemistry, and that is diamond, graphite, and silicon dioxide, which we're going to go on to very soon. Someone is saying, isn't HCl a compound? Exactly, it is. So remember I mentioned earlier that simple molecules can either be elements or compounds. It depends if they're made of more than one atom, or more than one element, sorry. So HCl is made of a hydrogen element and a chlorine element, so therefore it's a simple molecule and also a compound. Okay, so we've answered this question. The next question then says a compound called sulfur hexafluoride with chemical formula SF6 is used to stop sparks forming inside electrical switches. Designed to control large currents. So it's used to stop sparks forming inside electrical switches, which are designed to control large currents. State why the properties of this compound make it particularly useful in electrical switches. So note how, first of all, we've got SF6 and it says compound. If we go to our periodic table, sulfur hexafluoride, sulfur is on the side of this red line, that means it's a non-metal, and fluorine is also on the side of this red line, so is a non-metal. So what we know straight away is that this is a covalently bonded structure, and it's not one of our giant covalent structures, therefore it is a simple molecule. Now they've said compound, and they're right, because in this case, the simple molecule is also a compound because it's made of more than one element. It's made of sulfur and fluorine. Exactly, brilliant. So people are saying it doesn't conduct electricity, which is excellent. So the reason that it's used to stop sparks is because simple molecules don't conduct electricity, and that is because they have no charge. So remember, electrons are shared, which means that there's no free electrons to move, and also that they have no overall charge. Okay, excellent. Someone did ask me about ionic bonding and what makes a giant ionic structure. So all ionically bonded compounds form giant ionic structures. If you go to last Friday's lesson, you'll see what the description of ionic bonding is and what ionic compounds make. Someone's asking me, how do you know it's a simple molecule? So as I said, all covalently bonded structures will either form a simple molecule or a giant covalent structure. There are 3 examples of giant covalent structures, that is diamond, graphite, and silicon dioxide, which we're just about to go on to, whereas all other covalently bonded non-metals form simple molecules, which can also be a compound depending on how many elements make up that simple molecule. Okay, so let's go on to our first giant covalent structure, and that is diamond. So I've got a picture of diamond here. So we are talking about the diamond that you find in jewelry. So diamond, first of all, has this structure here. And what we can see, first of all, is that it is a covalent structure. And the reason for that is that these black blobs are carbon. So all that diamond is made of is carbon. So it's carbon bonding together. Now, does someone want to tell me, is this an element then, or is this a compound? So it's a giant covalent structure, but is it an element or is it a compound? It's only made of carbon. Exactly correct. Everyone's saying element. That is brilliant. And that's because it's only made of one element. It's only made of carbon, so it's not a compound. So the difference between an element and a compound is it must be made of two elements which are chemically combined. So if we have a look here, we can see that it's only made of carbon, therefore it's an element. So that's the first thing. The second thing is, let's have a look at these bonds. So what we can see is that all the carbon atoms are bonded together, which wouldn't normally happen. So therefore, if we think about our periodic table says that carbon has an atomic number of 6. So if carbon has an atomic number of 6, that means there are how many electrons in the outer shell? If there are 6 electrons, that's the atomic number. How many electrons are in the outer shell of carbon? Excellent. So everyone's saying 4. That's brilliant. So that means if we draw the electron structure of carbon, there are 2 electrons in the first shell and 4 electrons in its second shell. So each carbon atom here is forming 4 bonds, and that's because there are 4 electrons. So what we know is that means that there are no free electrons. They're all being used in bonding. And we're going to come on to what that means in just a second. So first of all, we can see the structure is made of lots of carbon atoms, all bonded together, and therefore there's no intermolecular forces. So usually, if for example we think about oxygen would form a covalent bond, and then there'll be weak intermolecular forces between oxygen molecules. Here, all the carbons, sorry, that should be an O, all the carbons are bonded. There are no intermolecular forces, there's all covalent bonding. And that is why the melting and boiling point of diamond is really high, because we don't break any intermolecular forces when we melt or boil diamond. We have to break covalent bonds. It also means that the structure is very hard, and that is because of those covalent bonds. So usually simple molecules don't have, they have intermolecular forces, and therefore they become gases at room temperature. And so we say that they're soft, if you want, whereas diamond is very, very hard because of these covalent bonds that need to be broken, and they can't be broken at room temperature. The final thing then is that it does not conduct electricity. And that is simply because there are no free electrons. So remember we said that carbon has 4 electrons in its outer shell, and it uses all 4 to make these bonds. So therefore it does not conduct electricity. Okay, so that's diamond. Just as a quick recap, it forms 4 carbon bonds. Someone's asking me, sorry, before I go over that, does diamond have stronger intermolecular forces? There are no intermolecular forces in diamond. There is only covalent bonding. Okay, so if you imagine this diamond here would just be a very large one of these structures. That's what that diamond would look like. There are no intermolecular forces. They're all bonded together covalently. And that's why it has a high melting and boiling point, because we have to break those strong covalent bonds, and it's hard and it doesn't conduct electricity because there are no free electrons. All 4 of carbon's electrons are being used in bonding. Okay. So the next thing is graphite. If we look at graphite then, first of all, what we can see is that it's also made of carbon. That's what it says here. So each of these black blobs are carbon, but it's got a very different structure to diamond. So graphite is used in pencil leads. So if we think about pencil leads, we know that graphite comes off onto the paper when we write with it. So therefore, it's classed as soft. And to think about why graphite is soft, we need to think about the structure. So in comparison to diamond, what we can see is that we've got these hexagons here. We call it a hexagonal structure. And that means if we look at each carbon, what we can see is that each carbon is only bonded to 3 other carbons. But we said that carbon's atomic number is 6, and therefore it has 4 electrons in its outer shell. So why is carbon only bonding to 3? Well, it's not about why, it's about what this means for graphite. What this means is that there is 1 electron from each carbon atom that is free to move. So in comparison to diamond, graphite will conduct electricity, and that is because one electron from each carbon atom is delocalized, which means that it's free to move throughout that structure. And then the other thing to think about is the melting and boiling points. So with most molecules, we only break intermolecular forces. Now, there are intermolecular forces in graphite, and that is between these layers. So graphite is made of layers of carbon atoms. This is one layer here, this is second layer, and then there would be 3, 4, 5, and there would be intermolecular forces between those layers. And what we can say is that when we melt or boil graphite, we don't break those intermolecular forces, we need to break the covalent bonding. So unlike simple molecules where we only break the intermolecular forces, even though graphite has intermolecular forces, both covalent bonding and intermolecular forces need to be broken in order to melt and boil graphite. So the main things about graphite, it's formed in layers of carbon atoms. It has a delocalized electron, so it can carry electricity. It still has a high melting and boiling point because we still need to break those covalent bonds. And it's soft, and that is because the layers of carbon atoms can roll over each other. And when they roll over each other, that can come off on paper as kind of your pencil mark on paper. So and that's because of those delocalized electrons and the weak intermolecular forces between layers, allowing those layers to roll over one another. So because of time, I think we'll cover silicon dioxide tomorrow, but for now we'll do some exam questions. So let's have a look at this question then. The picture shows a student using a pencil to complete a multiple choice answer sheet. The pencil contains graphite. Graphite rubs off the pencil onto the paper. So we can see here they've drawn a structure of graphite for you. Use diagram 2 and your data sheet to help you name the element from which graphite is made. So we've just covered that. Does anyone know what element makes up graphite? Yep, excellent. It's made of carbon. Brilliant. So that would be the first answer here. Okay. It says, use diagram 1 to help you explain why graphite can rub off the pencil onto paper. So why does graphite then, why can we rub off the pencil onto paper with graphite? Using its structure. So I'll go back to the structure here. Does anyone know why can we use graphite to rub off onto paper? Excellent. So the layers can slide over one another, and it's because of those weak intermolecular forces that the layers can slide over one another. So the 2 marks come from the layers of carbon atoms can slide over one another, and that's because of, the weak intermolecular forces. Okay, and what about part C? I'll just put weak intermolecular forces there. And that's between the layers that those forces are going. So part C says, draw a ring around the type of bond which holds the atoms together. And yep, exactly, it's covalent bonding because we're thinking about carbon. Okay. All right, the next one then, we won't do this one because it's silicon dioxide. We can do this. So diamonds are used as abrasives. The model there shows a part of the diamond structure. Diamonds are very hard. Explain why. So thinking about what we've taught today on diamonds, why are diamonds so hard? Brilliant. So people are saying strong covalent bonds. Someone's asking me what's an abrasive. So abrasive, if you think about, so there's lots of different definitions of abrasives. So if you think about cleaning products, so it can be abrasive in that it can be used as almost like rubbing and cleaning things off. And so it's, the proper word that I would use kind of to describe abrasive would be kind of almost like corrosive in that they can remove things. So if we think here, diamonds are used as abrasives, they can remove things. So we need to think why diamonds are very hard and why they can do that. So if you think about sandpaper, that's also quite abrasive. So that's almost kind of what the meaning of abrasive is. So diamonds are very hard, and why is that? So everyone is saying that there are these strong covalent bonds. Yep, so what we need to think about here is saying that there are strong covalent bonds between the carbon atoms. They form 4 covalent bonds. That's really important that we say each carbon atom forms 4 covalent bonds with other carbon atoms, and that they're very strong and require a lot of energy to break those bonds. So diamond is really very hard. Excellent. Okay, exactly. There are no intermolecular forces in diamond, which is very good. Okay, let's do one more question before we move on to the Q&A then. So here it says that graphite is softer than diamond. So we've explained why diamond is hard. Why is graphite soft? Does anyone know why graphite is soft? So it's not to do with the delocalized electrons making it soft. Yeah, it's because of the weak intermolecular forces. So the weak intermolecular forces between the layers mean that graphite is soft. Diamond doesn't have any of those intermolecular forces, and so it only has those covalent bonds which make it hard. Excellent. Well done. Okay, so if we move on to the Q&A, and then we can do another exam question while we're waiting for Q&A questions.
Thanks, Aman. Just having a look, there are some questions asking, can you explain why covalent bonding doesn't conduct electricity?
Yep. So if I go back to our simple molecules. Okay, so this is the page on simple molecules. And the reason that simple molecules or covalently bonded structures, so I just want to make a distinction here. So when we do covalent bonding, we can form two things. We can form a simple molecule, or we can form a giant covalent structure. So giant covalent structures are like what we've just covered, so diamond, graphite, and silicon dioxide, which we will cover tomorrow. And simple molecules are things like water, oxygen, nitrogen gas. And in giant covalent structures, diamond doesn't conduct electricity because there are no free electrons, but graphite does because there is one delocalized electron from each carbon atom. So remember I said that graphite forms only 3 bonds, whereas graphite has, or carbon atoms have 4 electrons in their outer shell, which means they can form 4, but they don't. And so that means that giant covalent structures, diamond doesn't, but graphite does conduct electricity, whereas in simple molecules, because electrons are shared, so if we imagine this nitrogen here, let me just get up let me go back to this page. So if we imagine this nitrogen here, what we can see is that the electrons are shared in that covalent bond. So those electrons have no overall charge, and it's all about the charge as to whether they can conduct electricity. So there's no overall charge on that nitrogen because electrons are being shared. They've not been gained, they've not been lost, and there's no free electrons in nitrogen molecules. Although you can see these electrons here, they're quite stable now because remember we formed 8 in its outer shell of electrons. So remember, if an element forms an outer shell of electrons, it becomes stable, it adopts a noble gas structure. So think about nitrogen here. It's got 6 electrons in the middle and 2 on the outside, which means each nitrogen element has formed 8 electrons in its outer shell. Therefore, it has a full outer shell of electrons and so is stable. So these electrons no longer want to bond or conduct any electricity. And that's why simple molecules don't conduct electricity.
Cool. And then another question on, can you explain again why diamond doesn't have weak intermolecular forces?
Yep, brilliant. I can go back to there. Okay, so this is the structure of diamond. So if we look at this diamond picture here, this diamond picture, or this diamond, would be made of a structure like this. All the carbon atoms bonded together. It wouldn't be made of like multiple of these structures. It would just be one big structure like that. And therefore, all the carbon atoms are bonded together covalently. So there aren't molecules, if that makes sense. It's all one big structure. So if we imagine a simple molecule like oxygen, oxygen molecules will have this double covalent bond between it, but the molecules have these weak intermolecular forces because oxygen goes around in pairs and there's lots of pairs in the atmosphere. It doesn't just go around as one pair. Whereas in diamond is made of this one big covalent structure. It's made of all these carbon atoms bonded together. There's no break there. There's not lots of these structures. It's one big structure. So there's no intermolecular forces because it's only one large molecule. And it's not technically a molecule, it's an element. It's one large element all bonded together.
Thank you. I had another question asking, are hydrogen chloride and hydrochloric acid the same thing?
So no, so hydrogen chloride is made of just hydrogen and chlorine. Remember, acids have different bonds in them. They've got the OH bonds, so they form the COOH bonds that we will come on to in a later lesson. So acids aren't just made of hydrogen and chloride, although when you write hydrochloric acid, you might see that written. It's not the same thing.
Okay, and then we've had quite a few questions asking if you can do another covalent question.
So another bonding diagram?
Yeah, another bonding diagram. I think that's what that means.
Okay, fine. Yep. So if we go to our periodic table then, let's try and do, let's do silicon fluoride. So silicon fluoride, if we look at silicon, first of all, silicon is in group 4 and it has an atomic number of 14. So if we draw silicon's electron shell diagram, there would be 2 electrons in the first shell, 8 in the second, 2 plus 8 is 10, and 4 in the final shell. So that means its last shell has 4 and it's in group 4, so that makes sense. Fluorine, on the other hand, is in group 7 and it has an atomic number of 9. That means there are 2 in the first shell and 7 in the second shell, and that makes sense again because it's in group 7. So if silicon and fluorine want to bond, we know that silicon wants 4 electrons to form its outer shell, whereas fluorine only needs 1. So that means for silicon to bond with fluorine, we have to bond with 4 fluorine particles, or 4 fluorine atoms, sorry. So it would look like this. So remember the Venn diagram structure. So fluorine will share 1 electron with each silicon, and silicon will also share 1. If we have a look at silicon now, it's got 8, and remember that fluorine already had 7, so if it's shared 1, that means there are 6 left. So if we look now at each fluorine, it has 8, so we've got 6 that are not bonded and 2 in the bond, which makes it 8. So that would be the covalent structure of silicon fluoride, and the chemical compound would then be written as SiF4. That's a covalent structure there.
Brilliant. And then we had another question following on from that, asking if you could do an exam question.
Yep, that's fine. Okay, we'll do this one. So explain why chlorine is a gas at room temperature, but sodium chloride is a solid at room temperature. So let's think first, what's the bonding that's going on between chlorine and what's the bonding between sodium chloride? So does anyone know what the bonding is between 2 chlorine atoms? If I go to the periodic table, that might help. So we've got chlorine and sodium chloride. Okay. Yep, exactly correct. Chlorine is made of covalent bonds, and sodium chloride, does anyone know what's sodium chloride made of? Yep, it's made of ionic bonds, and that is because sodium is a metal, chlorine is a non-metal. Okay, so that's the first thing to understand then, what type of bonding is occurring. So we know that chlorine is made of covalent bonds, and sodium is made of ionic bonds. So this is asking to explain why chlorine is a gas at room temperature, but why sodium chloride is a solid at room temperature. So if we start with chlorine, chlorine is made of these covalent molecules. So the first thing is, what changes chlorine into a gas? That phase is boiling. So we must say that the boiling point of chlorine is low. And that is because of the weak intermolecular forces between chlorine molecules. So remember, even though there's covalent bonding within a chlorine molecule, between different chlorine molecules, so if you imagine like this, there are weak intermolecular forces, and that is why the boiling point of chlorine is low. So you would lose a mark here if you said melting point, because this question is specifically saying, why is it a gas? So remember that it's the boiling point of chlorine that has to be low then to make it into a gas. So the boiling point of chlorine is low, and that's because of the weak intermolecular forces between the chlorine molecules. Okay, if we think about sodium chloride and why that's a solid at room temperature. So sodium chloride, which is NaCl, has a high And here we're going to say melting point because it's a solid, which means for it to turn into a liquid, it has to be a high melting point. So it has a high melting point, and that is because of those strong ionic bonds. And remember that the forces between ionic bonds, there are electrostatic forces or electrostatic attractive forces between oppositely charged ions. And so the melting point of sodium chloride is high, and that's why it's a solid at room temperature. So just as a quick recap of ionic bonding, remember that you form this structure with positive and negative ions like this. Someone is saying sodium chloride has strong electrostatic forces. Exactly, well done. Someone is asking, does ionic bonding have intermolecular forces? It does not have intermolecular forces. It's not made of molecules. Remember, intermolecular forces is only in simple molecules, and at the moment, graphite that we've covered has intermolecular forces. Yeah.
Lovely, thank you. Someone's asked if you can return to the page where there was a question about diamond.
Yes. Was it this one?
Yeah, I think that's the one they meant.
What did we want to know about this?
I think they just wanted to have a look at it. They haven't said anything else. Anything about that? Cool. So I think we have a couple of minutes left. There are some general questions here. Someone's asked if you will be able to join live group tutorials on your mini iPad. I think the best way to join them is if you do have a laptop, and it's fine if it's not a question related to chemistry in this instance, but the best way probably is to join them on a laptop or desktop. However, you can have a go on your mini iPad and see if it works. Someone else has asked if this session is recorded. Yes, and if you've signed up to the My Tutor online school, then you'll be able to get the links to them. I think a question for you, Aman, is in the chat. Could you explain again why HCl and hydrochloric acid are different? I don't understand.
So hydrochloric acid has a water bond in it. So if we dissolve hydrogen chloride in water or in an acidic substance, it becomes hydrochloric acid. So hydrochloric acid has other bonds in it. It has an OH bond, and that's what I was trying to represent with the COOH. So it's got a water bond in there, as well as the carbon bond, which you can sometimes find in hydrogen. The reason it doesn't have that carbon bond is because it's hydrochloric acid, so it would just have the HCl and the water bond in there. Hydrogen chloride is not dissolved in water, so it's just hydrogen and chlorine. So it's all about whether it's been dissolved in water.
Fab. I don't think there's any new questions coming through. We have 2 minutes. Oh, yeah, there is a question. When is A-level coming out for all topics? So we do, as I said before, we do want to try and expand to other level areas, and we'll be trying to do that shortly. But at this point, you just have to, if you've signed up to the online school, then make sure that you've keep checking all the updates on there to know exactly when that will be available.
Just to clarify, it is 9:45 this week for the chemistry sessions. And intermolecular forces, they are the forces between molecules. So there's a few different meanings. In graphite, if I go back to graphite, here it's the forces between layers. So if you imagine this is one molecule almost, because all the carbon atoms are bonded together, that is one molecule. And therefore, these intermolecular forces are acting between another layer or another molecule. In simple molecules, which is what most nonmetals will form, if you think about chlorine, it goes around in pairs like this, and there's a single covalent bond between chlorine atoms. We don't break those covalent bonds, we break intermolecular forces. So chlorine, you wouldn't ever find it as just one pair. You would always find it as lots of different chlorine pairs. and it's the bonding between all these chlorine pairs that's known as intermolecular forces. So it's the forces between a molecule. So this is one molecule, and then this would be a second molecule here, this would be a third, and it's the forces between molecules that are called intermolecular forces, and they're very weak.
Great, thanks, Aman. Cool. So I think that's the time for today. Thank you everyone for joining us, and we'll see you again tomorrow for another chemistry session, as Aman said, at 9:45. This has been recorded, so you can watch it back once the link is made available. Thanks everyone. See you shortly for the other sessions we have today. If you're sticking around for English, that's at 11 o'clock. Bye.
Thank you.